At 3,000 feet, engulfed in the pitch-black core of a midnight weather system, the human mind searches for stability. But inside the cockpit of a modern commercial airliner holding over a storm-battered city, the only reality comes from the glowing glass panels of the flight deck. Rain hammers violently against the windshield, sounding like handfuls of gravel thrown at high speed. The autopilot is engaged, maintaining a precise orbital holding pattern, a literal racetrack in the sky. To the 162 passengers sitting just on the other side of the reinforced cockpit door, this is nothing more than an annoying delay. They are resting, watching movies, complaining about a misconnection. They have no idea what is happening on the engine indicating and crew alerting system, the digital display located dead center between the captain and the first officer. Suddenly, an amber caution message populates on the screen. It does not flash rapidly. It does not trigger a screaming alarm. It triggers a single, subdued chime. Ding. For letters illuminate. Fuel low. The first officer, his eyes tired from scanning the weather radar, immediately calls up the system schematic on the lower display. The numbers are unmistakable. The center tank has been dry for an hour. The outer wing tanks are practically vapors. Only the inner main tanks hold the remaining highly volatile jet of fuel. The captain, a veteran with 12,000 hours of flight time, places a finger on his electronic flight bag tablet. He runs the burn rate calculation one more time. He factors in the density of the fuel, the drag of the heavy, turbulent air, and the exact burn rate of the two high bypass turbofan engines strapped to the wings. The result is chilling. 7 minutes. They have exactly 7 minutes of fuel before they dip below the absolute critical minimum reserve, a hard physical boundary where the fuel scavenge pumps inside the tanks begin to suck nothing but air, leading to a dual engine flameout. Over the radio, the sterile voice of the approach controller cuts through the static. Expect further delay. We have severe weather congestion on the approach corridor. Hold your current position. The captain looks at the first officer. The math is undeniable. 7 minutes until the engines starve. 7 minutes between a routine flight and a catastrophic urban glider scenario. The margin for error has just been erased. To understand how a multi-million-dollar, highly advanced commercial airliner ends up flying with only a handful of minutes of liquid thrust remaining in its tanks, you have to completely unlearn how you think about fuel. When you drive a car, you fill the tank to the top, and you drive until the needle hits empty. In commercial aviation, filling the tanks to the top is not just financially ruinous, it is aerodynamically dangerous. Every single pound of fuel loaded into the wings adds weight. Weight increases drag. More drag means you have to burn more fuel just to carry the fuel you just loaded. It is a vicious cycle of physics that aeronautical engineers fight every single day. Therefore, an airliner never flies with a full tank unless it is flying across an ocean. Instead, the amount of fuel loaded before departure is a surgical calculation governed by strict Federal Aviation Administration regulations, specifically Part 121. Before this flight ever left the gate earlier that day, the dispatcher and the flight crew agreed on a very specific fuel load. They did not measure this in gallons. In aviation, volume changes with temperature. Cold fuel shrinks, warm fuel expands. So engineers and pilots measure fuel exclusively by weight in pounds. The fueling manifest included several precise categories. First, the trip fuel. This is the exact amount required to take off, climb, cruise, descend, and land at the destination airport. Second, the contingency fuel. A small buffer, usually around 5% of the trip fuel, added just in case the winds aloft are slightly stronger than the weather forecast predicted. Third, the alternate fuel. If the primary destination is closed due to a sudden runway closure or weather, the aircraft must legally have enough fuel to fly to a designated backup airport. And finally, the final reserve fuel. This is the sacred, untouchable buffer. It is enough fuel to fly for exactly 45 minutes at a holding altitude. Under normal circumstances, an aircraft lands with its alternate fuel and its reserve fuel completely untouched. It is basically an insurance policy stored in the wings. when a fuel truck pumped thousands of pounds of jet fuel into the underwing receptacles earlier that afternoon. The tanks were perfectly balanced. The weather forecast for the destination was acceptable. Scattered clouds, a chance of late evening thunderstorms, but nothing that would shut down a major international hub. The flight took off normally. The 162 passengers settled in for a completely average domestic route. But aviation is an unforgiving environment where conditions change faster than human anticipation. The first domino in this chain of events did not fall near the destination. It fell thousands of feet in the air hours before arrival. As the airliner cruised at 35,000 feet, a massive thermodynamic shift was occurring ahead of them. A cold front was colliding violently with unseasonably warm, moist air rising from the surface. Cumulonimbus clouds, the heavy anvils of the sky, were building at a terrifying rate. By the time the aircraft began its initial descent, what was supposed to be a standard scattered thunderstorm had mutated into a solid, impenetrable wall of severe weather directly over the destination airport. Downdrafts, lightning, and extreme wind shear alerts lit up the screens at air traffic control. For safety, the tower did the only thing they could do. They temporarily closed the runways. No departures, no arrives, just a total halt of operations until the violent cell passed. In the sky, air traffic control began grabbing arriving aircraft and stacking them. They issued holding instructions. A holding pattern is a standardized racetrack-shaped flight path. The aircraft flies straight for a minute, executes a perfect 180-degree standard rate turn, flies straight for another minute, and turns again. It is an aerial waiting room. Our aircraft was directed to enter a hold at 10,000 feet. When the captain briefed the passengers, he kept his voice calm and reassuring. Ladies and gentlemen, the airport is currently under a heavy weather system, so air traffic control has asked us to hang out up here for a little while. We have plenty of holding fuel, and we expect them to clear us for landing shortly. He was not lying. At that moment, they had their contingency fuel, their alternate fuel, and their reserve fuel. But the clock was ticking, and jet engines do not run on optimism. Orbiting in a holding pattern is incredibly taxing on an aircraft's fuel reserves. At 10,000 feet, the air is much thicker and denser than it is up at cruising altitude. To push a 70,000-pound aerodynamic metal tube through this thick air, the engines have to work harder. The fuel flow meters on the center display were showing thousands of pounds of fuel being vaporized and turned into thrust every single hour just to fly in circles. Every time the aircraft banked to make a turn in the holding pattern, it lost lift, meaning the auto throttle had to automatically spool up the engines slightly to maintain altitude. Burn, turn, burn, turn. The digital fuel readout steadily ticked downward. Inside the cockpit, the atmosphere shifted from routine monitoring to intense strategic calculation. The first officer continuously updated the bingo fuel. Bingo fuel is an aviation term for the absolute point of no return. It is the exact number of pounds required to safely exit the holding pattern and divert to their chosen alternate airport, landing with their 45-minute final reserve legally intact. "We are still within limits," the first officer stated, running his finger down the weather radar display. But the severe weather cell below them was not moving. It was stalled, and because it was stalled, other aircraft in the area were also being stacked into holds. The airspace was becoming congested. Then, the situation deteriorated further. A sudden shift in the jet stream pushed high-altitude winds directly against the aircraft's holding pattern. To maintain their position, the plane had to fight a brutal headwind on one leg of the racetrack. More thrust, more fuel burn. The gap between their current fuel on board and their bingo fuel was rapidly shrinking. It was a mathematical vice grip. If they leave the hold right now and fly to their alternate airport, they survive but disrupt the travel of all 162 passengers, dealing with hotels, displaced crew, and massive airline expenses. If they wait just 5 more minutes, hoping the storm clears, they risk dropping below their legally required diversion fuel. This is where the true pressure of the captaincy sits. A 12,000-hour pilot knows that pushing a fuel limit is the easiest way to end a career, or worse, end lives. The captain made a decision. Check the weather at the alternate, he commanded. The first officer typed the request into the flight management computer. Moments later, the digital data uplink printed a small strip of paper on the center pedestal. The first officer ripped it off and read it. Sir, the storm front is expanding. The alternate airport is now reporting low visibility and gusting crosswinds. It is still open, but the approach will be slow. The vice closed completely. If they divert to the alternate now, they will have to battle a headwind to get there, and they might be put into a holding pattern there as well because of the degrading weather. Diving for an alternate is no longer a guaranteed safe escape route. Right at that exact moment, air traffic control broke through the radio chatter. Good news. The severe weather cell over the primary destination is finally breaking up. We are beginning to sequence aircraft for the instrument landing system approach. The tower is opening the runways. Relief washed over the cockpit, but it was incredibly brief. They were finally cleared to exit the hold and begin their descent. But there was a massive problem. They were not the only airplane waiting. Dozens of heavily loaded wide-body and narrow-body jets were funneling into the same narrow approach corridor. Air traffic control had to vector them, making them fly a longer, drawn-out path to ensure safe separation between planes. The captain looked at the fuel totalizer. It was dropping faster than expected. The dense air, the anti-ice systems drawing hot bleed air from the engines, the turbulence rocking the plane, it was all sucking efficiency out of the airframe. The amount of fuel left in the tanks was now intersecting dangerously with the time required to fly this extended approach path. As they descended through 3,000 feet, that amber message illuminated on the display. Fuel low. It is important to understand what this warning actually means from an engineering perspective. An airliner wing is not just a hollow box. It is a highly complex system of ribs, baffles, and surge tanks designed to keep liquid fuel pooling exactly where the primary boost pumps can ingest it. When fuel gets critically low, there's a very real physical danger called fuel unporting. If the aircraft hits severe turbulence or banks sharply, the shallow puddle of fuel left in the wing can literally slosh away from the intake valves. If the pump sucks air for even a few seconds, the high-pressure fuel lines lose pressure, the atomizers in the combustion chamber go dry, and the jet engine instantly flames out. To prevent this, low fuel warning systems are incredibly conservative. They activate well before the tanks are truly bone dry, but they serve as a harsh, screaming warning that you are now entering the absolute limits of the aircraft's design. The first officer tapped the glass display. "Captain, we are reaching minimums." The captain nodded. The time for passenger comfort and standard procedures was over. He pressed the push-to-talk switch on his control yoke. "Approach. This is a declaration of minimum fuel." Minimum fuel is a very specific, legally defined phrase in American aviation. It is not an emergency declaration. It is not a mayday. Declaring minimum fuel tells the air traffic controller one vital thing. My fuel supply has reached a state where I can accept absolutely no further delays. I cannot accept a vector that takes me off course. I cannot accept another holding pattern. If you delay me even slightly, this will immediately escalate into a full-blown fuel emergency. In the radar room on the ground, the approach controller heard the phrase. He looked at his screen. He had a heavy Boeing aircraft directly in front of our minimum fuel flight, moving slightly slower on the glide path. If he allowed things to continue naturally, our flight would get dangerously close to the heavy aircraft's wake turbulence. Usually, a controller would tell the trailing aircraft to slow down or do a small 360-degree turn to create space. But the controller knew the rules. Minimum fuel meant no turns. No dilas. The controller rapidly commanded the heavy aircraft ahead to keep its speed up until the last possible second. To our flight, he said, "Understood minimum fuel. You are cleared for the localizer. Maintain present speed. Contact tower." Inside the cockpit, the tension was absolute. The cockpit voice recorder captured only the sound of heavy breathing, the rhythmic thumping of the windshield wipers, and the electronic mechanical hum of the flight deck systems. The captain reached down and pulled the speed brake lever to manage their descent. The heavy metallic clatter of the landing gear deploying echoed through the fuselage. 3 green lights illuminated. Gear down and locked. The first officer set the flaps to the full landing configuration. This is where the physics of aviation become deeply unforgiving. An airliner in the landing configuration, with a massive landing gear hanging down and the massive wing flaps fully extended into the slipstream, creates a staggering amount of aerodynamic drag. It is essentially flying like an open parachute. To keep the aircraft flying in this dirty configuration, the engines have to maintain a high level of thrust. High thrust at low altitude means they were currently burning fuel faster than at any other point in the entire flight. The fuel totalizer was literally counting down pounds by the second. They intercepted the glide slope at 1,500 feet. Outside, the darkness was absolute, broken only by the strobe lights reflecting off the thick rain clouds. And then, the final hurdle arrived. As they dropped below 1,000 feet, the weather radar detected a sudden, violent microburst collapsing from the edge of the decaying storm cell. A massive wall of downward, plunging air slammed into the ground ahead of the runway and curled outward. This is wind shear. It is the most lethal invisible force in low-altitude flying. The airspeed indicator on the primary flight display suddenly surged forward by 20 knots, then immediately began rapidly dropping. The aircraft bucked violently. The autopilot fought instantly to maintain the glide path, pitching the nose down, then pitching violently up. In the cockpit, a harsh robotic voice triggered from the ground proximity warning system. Wind shear, wind shear, wind shear. The rulebook in commercial aviation is written in blood. Every pilot is trained with a single, unshakable directive. If you encounter severe wind shear on final approach below 1,000 feet, you do not attempt to land. You immediately push the thrust levers to maximum power, press the takeoff go-around button, pitch the nose to 15 degrees, and climb away from the ground. It is an automatic reflex. An aborted landing is always safer than fighting unpredictable aerodynamic instability near concrete. But go-around is a massive thermodynamic event. Spooling the heavy turbofan engines from approach idle all the way to maximum takeoff thrust requires an enormous volume of jet fuel. The fuel control units command the engine pumps to flood the combustion chambers. If this crew executed a standard go-around right now, fighting the drag of the landing gear and flaps until they could retract them, they would instantly burn hundreds of pounds of fuel in a matter of seconds. The first officer's hand instinctively moved toward the thrust levers, ready to assist the captain in a go-around. But the captain froze. He glanced rapidly at the fuel totalizer. If they initiated a go-around, shoved the throttles to the firewall, and climbed back into the turbulent holding pattern to try again, they would literally exhaust the remaining fuel in the tanks before they could complete the circuit. A go-around would mathematically guarantee a dual-engine flameout over a populated metropolitan area. They had passed the final invisible threshold. They could not go back up. They had to land, right now, on this piece of concrete through the wind shear. 7 minutes of fuel remaining. That was the reality. I have the aircraft, the captain barked, instantly disengaging the autopilot. A loud cavalry charge alarm blared, indicating manual control, which the captain silenced with a thumb switch. He wrapped both hands around the control yoke. He disconnected the auto throttles. He was now flying the 70,000-pound machine purely by human instinct, muscle memory, and the visual cues piercing through the rain. The wind battered the fuselage. The right wing violently dipped. The captain aggressively counter-steered, using the ailerons and rudder to force the nose back onto the centerline. The aircraft was descending like a falling leaf, fighting a massive crosswind. 500 feet. The automated voice counted down. The captain worked the thrust levers manually, making massive rapid adjustments to keep the airspeed from bleeding off during the shear. 400, 300, minimums. Through the pouring rain, the brilliant white and green approach lights of the runway suddenly pierced the darkness. They were slightly off the centerline, drifting fast to the left. 200 feet. The captain stomped the right rudder pedal, yawing the nose to align with the concrete. while keeping the wing dipped slightly into the wind to prevent drifting. It is a highly complex cross-control maneuver called a forward slip, executed while hurtling toward the Earth at 140 miles per hour. 100, 50, 30. The captain eased the throttles back slightly. Retard, the computer demanded. 20, 10. With a tremendous jolt that sent vibrations violently up through the seats and down the spine of the entire airframe, the main landing gear smashed into the wet, grooved concrete. The captain instantly slammed the thrust reversers open. The engines roared into life, redirecting their bypass air forward to decelerate the massive weight. He pulled the speed brake lever all the way back, deploying the massive spoilers on the top of the wings, destroying all remaining lift and putting the full weight of the aircraft onto the braking tires. The anti-skid system rapidly pulsed the carbon brakes, fighting against hydroplaning on the flooded runway. The deceleration threw the passengers violently forward into their seatbelts. It was not a smooth landing. It was a controlled, calculated drop to ensure the aircraft stuck firmly to the runway in high winds. The speed decayed. 80 knots, 60 knots. The captain smoothly closed the thrust reversers. The engines returned to their quiet, normal idle hum. They taxied off the runway and came to a stop on the nearest taxiway. The captain set the parking brake. The heavy silence that suddenly enveloped the cockpit was absolute. Neither man spoke for a solid 10 seconds. The adrenaline was slowly draining from their bloodstreams, replaced by the crushing exhaustion of immense psychological strain. The captain leaned forward and slowly exhaled a long, shaking breath. He looked down at the lower display panel. The fuel indication for the center tank read 0. The left main tank read roughly 600 pounds. The right main tank read roughly 600 pounds. Total fuel on board, 1,200 pounds. For the 162 passengers unbuckling their seatbelts in the cabin and cheering for surviving a bumpy landing, 1,200 pounds of jet fuel sounds like a massive amount. It sounds like a large reserve. But to the maintenance engineers who build and repair these machines, 1,200 pounds is nothing. When you factor in the physical space of the wing tanks, the unusable fuel that sits below the intake pumps, and the massive burn rate of 2 jet engines, 1,200 pounds equates to almost exactly 7 minutes of flying time. 7 minutes before the engines would have spooled down in total silence. 7 minutes between a safe arrival at the gate and a tragic leading news headline. The actions of the crew that night were heavily investigated by aviation authorities. It is standard procedure whenever a commercial flight lands below its final reserve limits. Flight data recorders were pulled. Radar tracks were analyzed. Dispatch fuel records were heavily scrutinized. But in the end, the official conclusion was clear. The flight crew committed no errors. The dispatcher committed no errors. The initial fuel load was completely legal and within all standard operating safety limits. This story is fundamentally terrifying not because someone made a colossal mistake, but because nobody did. Everyone followed the rules perfectly. But aviation is an inherently dynamic environment where unpredictable weather patterns, air traffic congestion, and aerodynamic drag can conspire to strip away layers of safety margins 1 pound at a time. The system did not fail. The system bent to its absolute theoretical limits, and then relying on the immense skill, manual flying capability, and split-second decision-making of a seasoned captain, the system worked. Aviation is heavily regulated because the margin between physics and disaster is microscopic. Every single procedure, from how engineers calibrate the fuel quantity indicating systems in the hangar, to how captains manage wind shear callouts in the sky, is designed to keep thousands of pounds of high-explosive liquid flowing seamlessly into spinning turbines. Aviation is not about completely avoiding risk. You cannot avoid risk when flying near the speed of sound at 35,000 feet. It is about aggressively managing that risk. It is about deeply understanding the mathematics of thrust and drag. And sometimes, in the darkest, stormiest skies, managing that risk flawlessly means making the hardest decision of your life, overriding instinct, landing through the sheer force of nature, and pulling up to the gate with precisely 7 minutes of life left in the wings.